morning. Myself, I'm Ganga Bhavani, Assistant Professor in EC Department of IARE. But today we shall discuss the topic feedback connection types and general characteristics of negative feedback amplifiers. Okay. So first we'll see what are the basic feedback connection types available. Okay. There are 4 basic ways of connecting the feedback signal. Right. Depending upon which signal, whether you are going to take voltage as feedback or current as feedback, as well whether you are going to give the feedback signal in series or in parallel. Accordingly, you'll have 4 types of feedback connection types. Those are voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. Okay. So in the list above, what we have seen, voltage refers to connecting the output voltage as input to the feedback network. So if you are taking output voltage as input to the feedback network, then you say it is voltage. It could be voltage series or voltage shunt, but the word voltage refers that you are connecting the output voltage as input to the feedback network. And the word current indicates, when you are saying current series or current shunt, what does the word current indicates? It refers to tapping of some output current through the feedback network. That is, your tapping of some output current through the feedback network. Now coming to the word series and parallel. Series refers to connecting the feedback signal in series with the input signal voltage. That is, if you are connecting the feedback signal in series with the input signal voltage, then it is series connection. Or shunt refers to connecting the feedback signal in shunt. Shunt is nothing but in parallel with the input current source. Okay. So the word voltage or current indicates whether the output voltage is given as feedback or whether output current is given as feedback. And the word series and shunt indicate whether you are connecting the feedback signal in series with the source or in parallel with the source. That is input voltage. So if you look at the types, see here. First one is A is voltage series, then this is voltage shunt, then this is current series, this is current shunt. So in voltage series, if you see, what are we doing here? In all the cases, A is a basic amplifier gain. This block indicates basic amplifier, and this is the feedback network, gain indicated by beta. So in all the 4 configurations, for the 4 connection types, A indicates a basic amplifier gain and beta is a gain of the feedback network. So in first case, if you see voltage series, what are we doing here? We are taking the output voltage V0 is taken as input to the feedback. Okay. So accordingly, you will have feedback signal is Vf. Now this Vf is connected in series with the source voltage. You can see this in series with the source voltage. So what you are calling it as voltage series feedback. And coming to the second one, here also it is voltage shunt. That is, output voltage is taken as input to the feedback network. Okay, V0 is taken as input to the feedback network, and output of this feedback network is, that is, current If. It is in parallel with the current source Is. Okay. So in voltage shunt feedback, in shunt connections, if you see, you will take current as a source Is, whereas in series connection, you are taking voltage as a source. Okay. So when you are taking voltage as a source, definitely the feedback signal also should be the voltage. So what you will have Vf and Vf in both voltage series as well as current series, you will be having Vf as a feedback signal. And coming to the shunt connection, whether it is voltage shunt or current shunt, you will be having current feedback signal, that is If as a feedback signal. In these both cases, Vf will be the feedback, whereas in shunt connection, If will be the feedback signal. Okay. Now in voltage shunt feedback, what are we doing? We are connecting this feedback signal If in parallel with the current source Is. So what you are calling it as voltage shunt feedback. And this one, current series feedback. Here we are tapping some current I0 as input to the feedback network. So I0 is given as input to the feedback network, but what will be the feedback signal? Feedback signal will be Vf, since it is series connection. Okay, so now Vf will be in series with is given in series with the source voltage Vs. Coming to the last one, current shunt. So here also current shunt means output current I0 is taken as input to the feedback signal. And coming to the output of the feedback signal will be in parallel with the current source Is. Okay, so you can see here it is given in parallel. In these 2 cases, it is given in series. In these two cases, it is given in parallel. So the only thing is, if it is voltage series or current series, if it is series connection, the source that you are taking is voltage source, and feedback signal also will be voltage signal only, VF and VF. Okay, and you are connecting the feedback signal in series with the input signal. Coming to this shunt configuration, whether it is voltage shunt or current source is taken as current is taken as source. So obviously the feedback signal also will be IF. Okay, and in both the cases, the feedback signal is connected in shunt with the input signal. You can see the difference here. These two are series connection. These two are parallel connection. So this is voltage series. Why? Because output voltage is given as input to feedback network. Here also output current is given as feedback to the input to the feedback network. So these two are voltage series, voltage shunt, current series and current shunt. Okay. Then we can just look at this summary table. Okay. So gain without feedback in case of voltage series, V0 by Vi. When you are seeing voltage series, output voltage is V0 and input voltage also is Vi. So V0 by Vi. Coming voltage series and current series, input will be Vi. Output will depend upon which or signal you are taking as output. Okay. So it is V0 by Vi, voltage shunt it is V0 by Ii, current series is I0 by Vi, and current shunt it is I0 by Ii. You can just see here. See, for voltage, for series connection, feedback signal is always Vf. Okay, and input signal is always Vin, Vf and Vin. Whereas for shunt connection, input signal is In, feedback signal also is Is. So accordingly, you will have these are the gains, gain without feedback and feedback gain, that is beta. For voltage it is Vf by V0. For voltage shunt it is If by V0. Current it is Vf by I0 and this is If by I0. Similarly, gain with feedback, that is when you are taking the whole circuit into consideration, that is basic amplifier as well as the feedback network, then the overall gain with feedback is given by V0 by Vs when it is voltage series, V0 by S when it is voltage shunt, current series it is I0 by Vs and I0 by Is. So this word voltage indicates output voltage will be V0. Similarly, voltage shunt, so output will be voltage, that is V0. Okay. Current series and current shunt, output will be I0, 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 I0. Coming to the input one, if it is series connection, you will have voltage as input. Okay, series connection, voltage as input. Shunt connection, current will be the input. Same thing with the feedback signal also. If this is Vi, feedback signal also will be Vf itself. Ii, so it is If. Vi, Vf, Ii, If. Okay. So once you get the gain of the feedback network beta, then you can find out overall gain, that is gain with feedback. Now series feedback connections will generally increase the input impedance, whereas shunt connections will tend to decrease the input impedance. Okay, and so series connection will increase the input impedance, shunt connections will reduce the input impedance, and moreover, voltage feedback will tend to decrease the output impedance, whereas current feedback will tend to increase the output impedance. In general, practical applications, what we prefer is input impedance should be high, output impedance should be low. From this, what can we understand? Using series feedback connection, we can increase the input impedance. Okay, and using voltage feedback, we can reduce the output impedance. So on the whole, if you use voltage series feedback connection, we can have high input impedance and low output impedance. So higher input impedance and lower output impedance can be obtained by using voltage series feedback connection. Okay, to obtain high input impedance, we need series feedback connection, as well as if you want low output impedance, you need to give voltage feedback. So on the whole, if you want to have high input impedance and low output impedance, then definitely we need to go with voltage series feedback connection. Okay. So next thing is general characteristics of negative feedback amplifiers. So till now we have seen what are the four basic network connection types: voltage series, voltage shunt, current series, and current shunt feedback connections. Okay. Then we'll just see what are the general characteristics of a negative feedback amplifier. So first thing we can see here is we'll have improved stability using negative feedback amplifier. How is it? Okay. So as we have seen in the earlier classes, we have seen gain with feedback is given by, for negative feedback amplifier, gain with feedback is given by AF equal to A by 1 plus A beta. Okay. Now, if we try to differentiate this with respect to A, dF by dA equal to, generally what is a formula for using U by V differentiation? V into U dash minus U into V dash by V square. So using that formula, if you write dF by dA, if you differentiate this dF with respect to A, you will get first UV, that is 1 plus A beta into derivative of A is 1 minus A into derivative of this 1 plus A beta with respect to A will give you beta. So A into beta by V square, 1 plus A beta whole square. So this will give you, on simplification, it will result in 1 by 1 plus A beta whole square. So DAF equal to, cross multiply this dA, you will get DAF equal to dA by 1 plus A beta whole square. So once you get DAF equal to dA by 1 plus A beta whole square, now if I divide both sides by AF, so DAF by AF equal to dA by 1 plus A beta whole square into, I'm dividing with 1 AF, so I'll just multiply by 1 by AF. Now on simplification, what do I get? dA by 1 plus A beta whole square into, see from this can I write AF equal to this, then what about 1 by AF? 1 by AF will be equal to 1 plus A beta by A. So 1 by AF, I am replacing this 1 by AF by 1 plus A beta by A. So now DAF by AF equal to dA by A. I am just trying to separate the terms, dA by A into 1 plus A beta by 1 plus A beta whole square. So one term will get cancelled, you will just left over with 1 by 1 plus A beta. So DAF by AF equal to dA by A into 1 by 1 plus A beta. Or the same, I can even write it as DAF by AF divided by dA by A equal to 1 by 1 plus A beta. Okay now. So this DAF by AF is called as fractional change in amplification with feedback. dA by A is fractional change in amplification without feedback, because AF indicates a gain with feedback and A indicates a gain without feedback. So DAF by AF is fractional change in amplification with feedback, and this is fractional change in amplification without feedback. Now this fractional change in amplification with feedback divided by, that is DAF by AF divided by fractional change in amplification without feedback, that is dA by A, is called as sensitivity of the transfer gain. So from the previous derivation what you have seen, this 1 by 1 plus A beta is nothing but called as sensitivity. So sensitivity is equal to 1 by 1 plus A beta. 1 by 1 plus A beta. Sensitivity is called as 1 by 1 plus A beta. This is called as sensitivity. So the reciprocal of sensitivity is desensitivity. So if you take reciprocal of this sensitivity, you will get desensitivity. So desensitivity is given by D equal to 1 plus A beta. Desensitivity is given by D equal to 1 plus A beta. So how can we say that there is stability in gain, or you are saying that improved stability? Improved stability means here the gain, finally the gain DAF by AF, it is dependent only on beta. Desensitivity is given by D equal to 1 plus A beta. Okay, fractional change in amplification with feedback is less compared to that of fractional change in amplification without feedback. You are able to see here DAF by AF equal to dA by A divided by something. So definitely it is reduced. Okay, fractional change in gain with feedback is reduced. Now, so if stability of the amplifier increases with increase in desensitivity, how? See, if A beta, generally A is far greater than 1. So if A beta is far greater than 1, Then we have AF equal to A by 1 plus A beta. So A by, when A beta is far greater than 1, I can just ignore this one compared to this sum. So A by 1 plus A beta is replaced by A beta. Then A get cancelled, you will have 1 by beta. So AF is equal to 1 by beta. So fractional change in amplification with feedback divided by fractional change in amplification without feedback is called as sensitivity. Okay. So AF is equal to 1 by beta. So in that way you can see that the gain with feedback with negative feedback is having good stability compared to that of positive feedback. Okay. The next we shall see how the distortion is reduced. Decreased distortion. First advantage what we have seen is improved stability. That is gain, change in amplification with feedback is lesser than change in amplification without feedback. Change in amplification factor without feedback. The next one is decreased distortion. So distortion of an amplifier with feedback. Feedback with feedback distortion is given by df equal to d by 1 plus a beta. So where d is total harmonic distortion without feedback. If without feedback distortion is d and with feedback it is d by 1 plus a beta. Generally 1 plus a beta is far greater than 1. So if you are dividing some number by a number which is far greater than 1, definitely the overall result will be lesser than this d. So d by 1 plus a beta will definitely be less than d. So what we can say that distortion of the amplifier with feedback, df is always less than, therefore we can say that df is less than d because it is divided by some factor 1 by, that is divided by 1 plus a beta, which is definitely greater than 1. So what using negative feedback connection can say that feedback distortion is reduced. Okay. The next thing is decrease in noise. So just as how we have seen equation for distortion with feedback, similar equation you have for noise with feedback. NF is equal to N by 1 plus A beta. So in this what can we say? NF equal to N by 1 plus A beta. Here N is nothing but noise without feedback. Okay. So noise with feedback is given by N by 1 plus A beta. That is, it is reduced by how much factor? 1 plus A beta. Okay. So same as case of distortion, here noise with feedback also is less than the noise without feedback. Negative feedback, it is noise will be reduced. So to go with input impedance and output impedance, first we'll have a general look about the block diagram of the negative feedback amplifier. So here this is a basic amplifier, right? Output of the basic amplifier, that is V0. It is sampled. Okay, it is sampled. That is part of the this output voltage will be given as input to the feedback network. It is sampled and given as input to the feedback network. Okay, and this output, overall output what you get, it is given across the load. It is given across the load. So this output voltage, whatever you are taking through the sampling network, okay, through the sampling device. Now this is given as input to the feedback network, whose gain is given by beta. So if you take this as voltage series connection, then it will be VF will be the feedback signal. So VF by V0 equal to beta, or VF equal to beta into V0, input signal into gain. So V0 into beta will give you the feedback signal. Okay. So this is given to the mixer. This is source signal. Source signal is now added with the feedback signal, added or subtracted based upon whether it is positive feedback or negative feedback. So after mixing, whatever output you get, that will be your input to the basic amplifier, VN. If it is current, it would be IN. Okay. So from this, we'll just try to define few things. We'll just show how input impedance will increase by using negative feedback amplifier. So let Ri be the input resistance without feedback and RIF be the input resistance with feedback. So with feedback, we are indicating this letter F. Ri is input impedance without feedback, whereas RIF is input impedance with feedback. So from this figure, we can see what is Ri. Ri is simply V in by I. If you take feedback into connection, then this overall circuit will have to take into consideration. Then Ri will be equal to how much? Vs by I. Vs by I. So without feedback, it is Vin by IN. With feedback, it is Vs by IN. Now RIF equal to, so from this equation I'll just write RIF equal to VS by IN. So Vs is equal to what? From the earlier equation, from this block diagram, you can see if it is negative feedback, Vs equal to, sorry, Vn equal to Vs minus Vf. If it is negative connection, this feedback signal is added with negative sign. So Vs minus Vf equal to Vn. So Vn equal to Vs minus Vf, or in other words, I can say Vs equal to Vn plus Vf. So now in place of Vs, I will just replace this Vn plus Vf by In. So RIF equal to Vn by In. Sorry, RIF equal to Vs by In. Vs by In. So Vs equal to Vn plus Vf by In. So Vn plus, and what is Vf? Feedback signal is given by Vf equal to beta into V0, because V0 is the input to feedback network and beta is gain of the feedback network. So output of the feedback network will be given by input into gain, beta into V0. So Vin plus beta V0 by In. So this is equal to Vin plus beta. What is V0? If you take the overall network V0 equal to A into Vin. See here, this amplifier output is given as V0. So V0 equal to input into amplification factor, Vin into A. Vin into A, amplification gain A. Vin into A will give you V0. So V0 equal to Vin into A. So this is RIF equal to Vin plus beta into V0 is A into Vin by In. So RIF equal to Vin, if I take Vin common on both the terms, Vin by In into 1 plus A beta. Okay. So if I take just Vin common in this term, Vin and Vin into 1 plus A beta by In. So RIF equal to, what is Vin by In? Vin by In initially we have defined it as Ra. So therefore RF equal to Vin by In is Ri into 1 plus A beta. Okay. So RIF is input impedance with feedback, whereas Ri is input impedance without feedback, and A is gain of the amplifier, beta is gain of the feedback network. So as we know that A beta is far greater than 1, so this 1 plus A beta is definitely greater than 1. So what will be the effect of input impedance RIF? So RIF is equal to Ri into some value greater than 1, means definitely this whole product also will be greater than Ra. Ra multiplied by something greater than 1, definitely it will be greater than Ra. So on the whole we can say that the input impedance with feedback is, so from this I can say RIF is always greater than Ri. That is, input impedance with feedback is greater than input impedance without feedback. Okay, so in this way we can say that negative feedback connection will increase the input impedance. Okay, next we shall see how it decreases the output resistance. So same as how we have shown for input impedance, now we'll try to write equation for R0F. Okay, so generally what is equation for V0? V0 equal to A into Vin plus I0 into R0. Okay, so A into Vin plus I0 into R0. For output resistance calculation, V is equal to minus Vf. Okay, since Vn equal to Vs minus Vf. Okay, so for output resistance calculation, Vn equal to minus Vf, then V0 equal to what? Minus A into Vf plus I0 into R0. Okay, so V0 equal to minus A into Vf plus I0 into R0, or you can say V0 equal to minus A. What is Vf? Vf equal to beta into V0. So it is minus A beta V0 plus I0 into R0, or V0 into, I'm just trying to take this term to the left hand side and take V0 common. V0 into 1 plus A beta equal to I0 into R0. So R0F equal to V0 by I0, that is equal to R0 by 1 plus A beta. Simply rearranging these terms, you will get this equation. Okay, so R0F, again output impedance with feedback, is equal to output impedance without feedback divided by factor greater than 1. So when you're dividing something by a number greater than 1, definitely the overall result will reduce. So from this I can just write that R0F is less than R0. So output impedance with feedback is less than output impedance without feedback. Okay. Then the last one, we shall see how the bandwidth increases by using negative feedback amplifier. Okay. So to see the gain at lower frequencies, if you see the gain at lower frequencies, AL equal to A by 1 minus JFL by F. Okay. And lower frequencies gain with feedback is given by this form. So ALF equal to AL by 1 plus AL beta. Okay. Generally, the gain at lower frequencies is given by this equation. AL equal to A by 1 minus JFL by F. And ALF equal to AL by 1 plus AL beta. That is gain at lower frequencies without feedback is given by AL. Okay, AL by 1 plus AL into beta. So this is equal to replacing AL by A by 1 minus JFL by F, A by 1 minus JFL by F, AL equal to this one by 1 plus AL into beta. So this is equal to A by, on simplification, you will finally see that this will reduce to A by 1 minus J FL dash by F, where FL dash is equal to what? FL by 1 plus A beta. See this. FL by 1 plus A beta, I am replacing it by FL dash. So what can you see? FL dash is equal to FL by 1 plus A beta. So simply you can see that the lower cutoff frequency FL, without feedback we have seen that lower cutoff frequency if you have assumed as FL. So trying to write the same equation here, ALF, that is at lower frequencies if you are writing the gain, it is given by A by 1 minus JFL dash by F. So FL dash is equal to this. So the lower cutoff frequency with feedback is given by lower cutoff frequency without feedback divided by 1 plus A beta. So again it is understood that lower cutoff frequency is reduced by a factor equal to 1 plus A beta. So initially this is FL without feedback. So when you take feedback into consideration, what is happening? Lower cutoff frequency is reduced by a certain amount. So FL dash will be less than FL. So similarly at higher frequencies, now FH will be more. Okay, we'll just see. AH at higher frequencies gain is given by A by 1 plus J into F by FH. At lower frequencies it was A by 1 minus J into FL by F. Here it is A by 1 plus J into F by FH. There it was FL by L, FL by F, and here it will be F by FH and with plus sign. So now AHF equal to, with feedback if you take, it is equal to AH by 1 plus AH into beta, that is A by 1 plus A beta form. Okay. Now simply substituting this AH again in both numerator as well as denominator. On simplification, you can reduce it into the form of A by 1 plus J F by FH dash. Okay. Now comparing this with without feedback and with feedback. Okay. Here FH and here you have FH dash. So this indicates the higher cutoff frequency with feedback. So what is FH dash equal to? FH dash is equal to FH into 1 plus A beta. See these two. Compare these two equations. These two sides. Then it is A by 1 plus A beta into 1 plus J F by FH. So okay, this is equal to A by 1 plus J F by FH dash. Okay. So you'll get FH dash equal to FH into 1 plus A beta. So from this, what do we understand? Upper cutoff frequency or higher cutoff frequency is increased. Yes, FH is multiplied by 1 plus A beta means definitely its value will be more. So FH dash is greater than FH. Okay. FH dash is greater than FH means if this is FH, FH dash will be somewhere greater than FH. So this will be your FH dash. This is FL dash. This is FL. This is FH. Okay. So FL is reduced and FH lower cutoff frequency is reduced and upper cutoff frequency is increased. So generally bandwidth will give it as FH minus FL. So FH minus FL without feedback compared to this width will be more, definitely more. So the bandwidth with feedback will be high. Okay. Of course, gain without feedback is more compared to gain with feedback. As you can see here, gain is high without feedback. Okay, but bandwidth is less. So the same thing when you use negative feedback connection, what will happen? Bandwidth will increase, but gain will reduce. Okay, the same thing we can see here. So this is FL and FHR, lower and higher cutoff frequencies without feedback. FL dash and FH dash are lower and higher cutoff frequencies with feedback. So as you can see, what is happening here? The bandwidth is increasing in case of feedback, but gain is reduced. Whereas without feedback, bandwidth is less, but gain is high. Okay. So these are the various characteristics of negative feedback amplifiers. So what are those? First thing was stability of gain. Okay. Then next one was distortion, decreased distortion. Then decreased noise. Finally, high input impedance, low output resistance, and at the end we have seen that increase in bandwidth. Bandwidth has increased as well as increase in bandwidth. Okay, by using negative feedback. So these are all the various characteristics of negative feedback amplifiers. Right. This is a reference that I have used. Integrated Electronics by Jacob Milliman. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.